all these indexes have already been dealt with. Or it wouldn't be insertion sort.
So we don't compensate or add with the previous ones that would have already been compared?
No. No, I'm just asking how many comparisons were done during the past where you put this thing into order.
Okay.
And you've got to assume that the previous passes have already occurred. The idea is if you answer that question for every index and add them together, that's how many comparisons were done for insertion sort at that time. Okay? Now, you didn't ask the question I thought you were going to ask, which is how do you go about coming up with these formulas for how many comparisons are done? So let's try that. This is the trick. I give you an example array of size 8. Usually that one array is enough to figure out the formula. We're n is 8, which means there's 9 things. So 1, 2, 3, 4, 5, 6, 7, 8, 9. The first element's always 0. So the thing to do is you're looking for a pattern. And this is what students do, which I think is a mistake. They'll figure out the total number of comparisons done to sort an array and write that down for n equals 8. Then they'll do the same thing for n equals 10 and n equals 12 and try to look for a pattern in those numbers. What you want to do is figure out how many are done for sorting this index and write some number down. How many are done for that index? How many are done for that index? And so on. Now suppose you did that and you came up with that right there. It was initially ordered such that it took one comparison to deal with this index, 2 for this one, 3 for this one, 4 for this one, and then 1, 1, 1, 1. Now, what would be an initial ordering that would cause that?
It would be like 4, 3, 2, 1, and then the rest are sorted 5, 6, 7, 8, 9 sorted.
Yeah. So that would cause that pattern. Okay, suppose I said the pattern is the small half the elements are in a descending order, and then the big half the elements are in ascending order. How many comparisons are done as a function of n, where n is the biggest number in the array. So what I would do is take the array of size 8, do this to it, say, okay, so the first one took 1 comparison, 2, 3, 4, and then the rest take 1s. And then, what's the pattern that you see? It should jump right out at you. Yeah?
So the first half is the summation from 1 to n halves, and
Okay.
then the second one is just plus n. Or n halves, yeah.
All right, so n is 8 in this case. So this sum here is n over 2. Those are n over 2 ones. This is just the sum 1 plus 2 plus
Summation of
plus n over 2. Okay? Now, if you had just reduced this all to a single number, what would you have? You'd have 14. Okay? You won't see a pattern with 14. So look for just do what I said here. Do it like that. And then how do you finally answer the question? How do you reduce it to an answer?
You simplify.
Yeah. So how do we simplify this? The sum of the first n over 2 integers. What's the sum of the first k integers? Remember, tattoo it. Tattoo it on your brain. Yeah.
N times n plus 1 quantity divided by 2.
Okay, so the sum of the first n integers is n times n plus 1 over 2. So what's the sum of the first n over 2 integers? Yeah.
n over 2 plus 1 over 2.
All right, n over 2 times n over 2 plus 1 over 2. So our total sum is this plus that. You just need to reduce it to a polynomial in n, and that's what you enter in the assignment. So it's going to be something times n squared plus something times n plus something. I'm not sure exactly what. So it would be plus 1/2.
So we'd be expected to simplify the multiplication on the numerator for n over 2 times n over 2 plus 1.
Absolutely. I want your answer to be in the form an squared plus bn plus c. I gave directions on how to format it. Okay, any questions about that or anything else? Yeah.
So I think on one of the problems
at least the math that I was looking at, I had a summation of 2 plus 4 plus 6
Okay,
up to n.
okay.
Can you assume that that would be the same thing as n times n plus 1 over 2, but that divided by 2 as well?
Okay.
Oh, never mind.
When we talk about how to simplify that, how would you simplify if you saw the formula 2 plus 4 plus 6 plus 8? How would you describe that?
Divided by 2.
Sum from 1.
2 times 1 plus 2 plus 3 plus 4. Okay? In all these summations of integer sequences, the trick is to simplify it to the sum of the first k integers for some k. We went through several examples of that in the slides last time, so you could go back and refer to those examples and how to simplify. So if you're, let's say you had this series, 2 plus 4 plus 6 plus n. How can we simplify that?
2 times 1 plus 2 plus 3 plus 4.
That's 2 times 1 plus 2 plus 3 up to n over 2. We just saw how to do that. So it's just twice this, not half that. Any other questions? Yeah?
When you were about solving that compiler error last time when you submitted for like question 4, what did you resolve in that? Because I'm kind of having the same.
When I was having trouble with catus,
Yeah.
my main method, I forgot to have the parameter to main be an array of strings. I just put string, the parameter is a string instead of an array of strings.
And also to remove package. When you would have
Oh, yeah, yeah. It didn't seem to like to have a class that was in a package. That's Java, though, so if you're not using Java, it's not an issue. Yeah?
For the program you have to write, you say that there's a secret test case that don't show that we passed. Would those be more of like exceptions that we have to handle, or maybe just like a greater number of integers that we have?
Okay, so first of all, there's no exceptions you have to handle.
Okay.
You can assume that the input is exactly as specified, so it's not like there's going to be missing input.
Okay.
It's just that the one thing is much larger input to make sure you're using an efficient enough algorithm.
Okay.
And also, if there are any edge cases, it may appear in those tests. Okay? So I've looked at a few that have been submitted on CAT. Look at the queue and see how it's going. And I see something that I see a lot is you take an algorithm that's really efficient, but it's not going to be efficient if one of the sub-steps is an n-squared algorithm or a very inefficient algorithm. And the one thing that I see is you got to sort your string, right? So how do you do that? How do you sort a string so the characters are in ascending order? Yeah.
You can put it as an array of characters.
Okay, you can convert it to an array of characters and then sort the array. And then how do you turn it back into a string? Depends what language you're using. But what won't work, very efficiently anyway, especially if the strings are long, which there will be when you test it, is something like this. So let S be your string, and we'll say for each character in the string, we're going to declare a result up here. Terrible idea. Okay? You don't get anything outside of this class. This is practical complexity. This is the sort of thing you need to train yourself to spot and avoid in your programming without having to wonder, why is this slow? You should just know that's going to be slow. Why is that slow? Yeah?
Strings are immutable, so it has to copy over every time.
Right. Strings are immutable. This does not append C onto a result. What this does is copy result with C added onto the end. So if your string is 100 characters long, okay, the first time you're copying an empty string. The next time through you're copying a 1-element string, then a 2-element string, then a 3-element string. And by the time you get to the end, you've done a lot of work. So something like that will kill your efficiency every time. So what you need to do is either find a method that directly converts from an array of characters to a string. I think Java there is probably a constructor that does that, a string constructor that takes an array of characters. Or use something like a string buffer, which is a mutable string,
That's what
where there is an append method. But yeah. Yeah,
So those constructors don't do this process implicitly?
no,
How would they do that?
they probably they may use a string buffer. But yeah, the folks that wrote Java aren't going to use, if there's a better algorithm, they're going to use it. But the folks that wrote the library. Yeah? Any other questions? Okay. Okay, last time we were talking about doubling behavior. And essentially what I told you was what I'm interested in when I look at an algorithm is its doubling behavior. What happens to the running time when you double the input size? And what we decided was that if you're only interested in doubling behavior, then you don't need the exact formula for the running time to figure out the doubling behavior. You just got to know what's the high order term. The low order terms don't matter in the long run, which is what we care about. And the coefficient of the high order term does not matter in the long run. It doesn't matter at all, really, because it just cancels out. And doubling behavior is, if you're interested in doubling behavior, then big O notation is a convenient way to go because there's a tight relationship between doubling behavior and what big O tells you. So when we say that a function f is O of n squared, f of n is O of n squared, we're saying several things. One thing is this is informally speaking. We'll do a formal definition later. What we're essentially saying is its high order term is no bigger than an n squared term. Okay? So is n squared O of n cubed? Okay? What's your reasoning? You say no, so what?
It's simply because no matter how big you get n squared, it will never surpass the same amount as
Right, but I said is n squared O of n cubed? Yeah. N cubed is bigger than n squared. Okay? So in this case, f of n is n squared, and we're asking is f of n O of n cubed? The higher order term is no bigger than n cubed. Or, to avoid the confusion with the slide, let me ask this. Suppose f of n is just n. Is n O of n squared? Yeah. The higher order term is no bigger than n squared. Yeah?
So according to that, we would also be making similar statements like log of n is n squared and n cubed.
No.
Because-
Log of n is O of n squared and O of n cubed.
Yes, sorry.
Okay? You can think of big O of n squared as being a set of all functions whose higher order term is no bigger than n squared. And I guess formally the right way to say it is f of n is a member of O of n squared. I like to say f of n is O of n squared. And I think what's really misleading is books that will write f of n equals O of n squared. That's really bad in my opinion. Okay? So we use big O to put an upper bound on the high order term of the running time or the space consumption or whatever we're trying to characterize of an algorithm. So it's just gives you a way to put upper bounds on things. So another way to talk about it is asymptotically. In other words, as n goes to infinity, f of 2n will be no more than 4 times f of n. So this is putting limits on the rate of growth. Or we may say f of n's rate of growth is less than or equal to n squared's rate of growth. Or n squared's rate of growth is an upper bound on f of n's rate of growth. What do I mean by rate of growth here? Yeah.
The number of comparisons it takes as you have larger and larger arrays.
Well, yeah, it doesn't necessarily have to be comparisons. We're talking about time. In this case, we're talking about time. So what I mean is doubling behavior. Rate of growth is doubling behavior. So if you double the size of the input, the running time will grow by 4 times or less if the thing is O of n squared. Okay? That's all it is. What's the tightest bound you can put on selection sort? In the worst case of selection sort. If say you're sorting n elements, what's the tightest upper bound you can put on the running time in the worst case of selection sort? Yeah?
O of n squared.
O of n squared. Okay? You can't, there's no smaller polynomial that'll work. There are bigger ones, but, and so we say that O of n squared is a tight number. It's as small as we can make it. Okay? Answer me the same question for an array with k elements.
It'd still be O of n squared.
Okay? So if you sort an array of k elements with selection sort, the bound is not O of n squared.
Be O of k squared.
O of k squared.
Sorry.
Okay? I notice that some students sort of think that the n doesn't stand for anything. It's just a random word. No, n has to be related to the problem somehow. So if I say there's k elements, I need a bound in terms of k. I just want to remind you of that. Okay? So that's big O. Yeah?
Is there a notation for the tightest bound, or do you just say it's the tightest bound?
Wouldn't it be omega?
If the upper bound and the lower bound are the same, then we can use theta. That's tight. But otherwise, sometimes you'll say the bound is O of n squared, and you would just say it, and it's a tight bound. Okay. So if we can bound from above, we need to be able to bound from below. And that's what omega is. So when we say that a function f of n is omega of n squared, we're saying its higher order term is no smaller than n squared term. It can be that small or bigger. And similarly, f of 2n is 4 times or higher than f of n in the long run. So all I did here was switch the sense of these yellow terms here. Like I turned this thing around from big O. This was upper bound before, now it's lower bound, and so on. So if f of n is O of g of n, what can you say about g of n? If f of n is bounded from above by, if the rate of growth of f of n is bounded from above by g of n.
That would mean that g of m is omega of f of n.
G of n is omega of f of n, yeah. They're inverses. So if one function, if f is O of g, then g is omega of f. And then there's theta notation. That just says that its higher term is an n squared term. If you say something is theta of n squared, you're saying its higher term is n squared.
Would it be appropriate to label f of n equals theta of n squared?
No, you'll see that. You'll see people use equals. I think it's misleading. Just is or is a member of. If you want to think of it as a set, then you would say f of n is a member of theta of n squared. If you want to think of it as a property, you would say f of n is theta of n squared. I think the equal sign is really misleading because you're equating two very different things. A function to a set of functions. Yeah?
Does that mean that it's always n squared?
Right. Well, if we say that if the function is theta of n squared, then yeah, it's no bigger than n squared, it's no smaller than n squared. It grows as n squared. So if f of n is theta of n squared, that means it's O of n squared and also omega of n squared. It's above and below the same. Okay, and we'll use all those notations quite a bit. But we're just using it to talk about doubling behavior. So let's look at the notations we have and compare them. So we've got big O, which corresponds to rate of growth is less than or equal to some upper bound. We've got big omega, which corresponds to greater than or equal to when you're talking about rates of growth. So if you're talking about rates of growth, what would be the right way to think about theta?
It's equal to.
Yeah. If you're comparing rates of growth, then it's appropriate to talk about equals. So if you're talking about comparing rates of growth, You got one thing that'll put an upper bound, one thing that'll put a lower bound, one thing that will put both on simultaneously. Now, what's missing from this chart? Yeah.
Unequal to?
Well, okay, what else is missing from this chart besides that?
The average?
No, not the average. Yeah?
Strictly greater than or less than?
Right, greater than and less than. And in fact, there's notation for that. We won't use this very much. There's little o and little omega. Little o means strictly less than. The rate of growth is strictly less than. So if we say, it's not true to say that n squared is little o of n squared, because the rates of growth are the same. You need to say n is little o of n squared. Little o is how we define, is how you characterize a low order term. A low order term is little o of a bigger order term. And then little omega is just the opposite. So the little o bound is guaranteed to be loose. Yeah, but we won't use those much. We'll use little o a little bit today and probably never again. We'll focus on the three in the middle. Yeah?
How often would you say terms such as little o or little omega would be used in the industry today, if at all?
Well, it depends what industry. In the software development industry, not at all. You mainly see little o and little omega in proofs. So here's some examples. There's our function, 3n squared plus 5n plus 3. So that thing is o of n cubed, it's o of n squared log n, it's o of n squared. Those are all great. The rates of growth of the things in the first row are all greater than or equal to the rate of growth of that guy up there. And how do we know that, informally speaking? Yeah? All right, we look at the high order term of the function, which is n squared. We throw away the low order term, we throw away the coefficient, we've got n squared left. Well, n squared is no bigger than n cubed, right? N cubed grows faster than n squared. N squared log n grows a little bit faster than n squared, and n squared grows the same rate as n squared, so that's why that's true, yeah.
So you give a function like that, but for like a real life example, so for insertion sort, we're supposed to get the number of comparisons as a function like that.
Yeah.
What about something like running time or number?
Well, that we could postulate that's the running time for insertion sort on some processor, I suppose, with undefined units. I mean, the notation works. It doesn't matter what you're computing. It's just a matter of what the function is, whether it stands for comparisons or time or space.
Yes, I'm just looking for like what's a standard metric to measure what to measure one algorithm against something else. I don't know.
Well, the standard measure is rate of growth. It's hard to say. I mean, you can talk it. You know, insertion sort tends to be about twice as fast as selection sort, so you might say that. But the time it takes for an algorithm to run on a processor is just totally dependent on how well it's implemented, what language is used, how good the compiler is, how fast the computer is. And so rather than stress too much about trying to say how long an algorithm takes, we talk about how does the time it takes depend on the size of the input. And that characterization is independent of what kind of computer we're using or what language we wrote it in.
Nice.
Yeah?
We're labeling this polynomial as big O of n squared, but are we just choosing to simply ignore the 5n and plus 3 that could possibly make its growth slightly larger than
Okay.
big O of n
Okay,
squared?
so he's looking and seeing that, okay, this is demonstrably larger at all points than n squared. So where do we get off saying that they grow at the same rate? Yeah?
Since those are constants, wouldn't it just be like just shifting it up or down, but not necessarily changing it?
Well, if you graph them, wouldn't the graph of this always be above the graph of n squared, except at 0? Well, not even, forget about 0, it's always above, yeah?
Well, as you approach infinity for n, the difference between that value and the value of n squared is negligible.
Right, so if you look at the doubling behavior of that thing there, for large n, you'll find out you double n, the value of that thing quadruples. I mean, not quite, a little bit more than quadruples, but The closer to infinity you get, the closer the doubling behavior gets to 4. Same thing is true of the n squared test.
So it's safe to pronounce that as big O n squared.
Yeah, absolutely. In the long run, they grow at the same rate. As n gets bigger, the lower order terms become insignificant. And the leading coefficient doesn't matter because if you compute a ratio between f of n and f of 2n, the leading constant is going to cancel out. That's an argument I tried to make last time about the doubling. Okay? It's not true to say that 3n squared plus 5n plus 3 is O of n log n, or O of n, or O of 1. Those are not upper bounds. Okay? On the other hand, it is true to say that it's omega of 1, or omega of n, or omega of n log n, or omega of n squared. Those are all good lower bounds, but you can't say this, because those aren't lower bounds. That thing is theta of n squared. They grow at the same rate, asymptotically. It's not any of those things, and so on. This, it's little o of n cubed, but it's not little o of n squared, because the bound there has to be loose. Yeah?
When would you ever want to call that equation like big O n cubed instead of big O n squared? It seems like you would always want to call it big O n squared. Just
Okay, that's a fair question. Why would we characterize that thing as O of n cubed when it's more precise to say it's O of n squared? Yeah?
My guess would probably be that sometimes you can't be perfectly accurate, so you can at least tell it's not going to go.
Okay, he said sometimes you can't be perfectly accurate. So yeah, if we're trying to characterize that thing right there, we would just say it's O of n squared. But sometimes you might have an algorithm and you can't figure out what the running time is. Exactly. All you know is that, well, it's certainly no better than n cubed. So you say it's O of n cubed. And then this happens all the time with algorithms that are first discovered. For an example, there was an algorithm discovered, I don't know, 15 or 20 years ago in India, which was the first algorithm to test whether a number was prime in polynomial time. And it started out being an O of n to the 12th algorithm, where n was the number of digits. And after a while, people improved on the analysis and on the algorithm and got it down to O of n to the 6th. So sometimes analysis is just too hard to get exacts, but you can put an upper bound on it. But if you can put a lower big O bound on it, you should. Yeah?
Something like quicksort, I'm wondering, is there like a formula that describes it, or you just have to use two formulas? Because it has, like, its worst case is
Okay.
n squared and its best case is n log n.
Right. So I'll get to that in a second. Okay. So you often use complexity notation, as he was suggesting just now, to put bounds on the running time of all of the cases of an algorithm. And when we do that, when we say that selection sort is O of n squared, what we're saying is the worst case for selection sort is O of n squared. Because if the worst case is O of n squared, that means every case is O of n squared, by definition of the worst case. Similarly, when we say that selection sort is omega of n squared, we're giving a lower bound on the best case, right? I mean, we're really giving a lower bound on all the cases, but it's enough to give a lower bound on the best case. And when the two are the same, it's O of n squared and omega of n squared, we can just say selection sort is theta of n squared. That means no matter the data, if you pick some array and sort it and draw the graph, you'll get an n squared curve. You double the size of the input, you'll quadruple the running time. So this applies when you're using big O notation, asymptotic function notation, to describe an algorithm, to characterize a running time or the space consumption or some property of an algorithm. You're putting upper bounds and lower bounds. Upper bounds on the worst case, lower bounds on the best case. So what does that say? No, let me do this first before we get to the next one. Okay, we've already mentioned that these bounds are not necessarily tight. Common misconception I get from students in here is that big O somehow means worst case. No, it means upper bound. It's often used to put upper bounds on the worst case, but it does not mean worst case. So it's okay to say, it's less precise, but it's correct to say that selection sort is O of n cubed and omega of n. We can put tighter bounds on than that, but those are definitely bounds. You can say that the worst case of selection sort is omega of n squared. What do we do when we say that? We're putting a lower bound on the worst case. So what are we saying when we say the worst case of selection sort is omega of n squared?
You're saying that
Yeah, back there.
The worst case isn't going to get any better than that, and it's also not going to get any worse.
No, you're mistaking that for theta.
Oh, right, that, it's not going to get any worse than that.
No, not going to get any better than that. This is lower bound on the worst case. So if we say that, we're just guaranteeing the worst case is n squared, or it could be n cubed, or it could be n to the fourth, it could be exponential.
Oh, right.
We're putting a lower bound on the worst case. So we're not saying very much. Okay? And when we say the best case is O of n squared, we're saying it's O of n squared, or it may be faster. So that's not a very useful thing either. But you can use big O notation to put upper bounds on anything, and big omega notation to put lower bounds on anything. That's the point. Usually you don't see that, but just when you see big O, think upper bound. When you see big omega, think lower bound. Okay, here's insertion sort, which is similar to your quick sort question. In the best case, it only does n minus 1 comparisons. So when does that happen with insertion sort? If the array is already sorted to start with, it'll do, for every element it'll do, except the first, which it doesn't even look at, it'll do one comparison and then no swap. One comparison and no swap. So in that case, in the best case, it does theta of n comparisons. In the worst case, it does n squared comparisons if the array is completely anti-sorted. So what can we say about the algorithm? How can we use big O and big theta to describe insertion sort? Because unlike selection sort, the best and the worst cases don't have the same rate of growth. Yeah?
You can say that its worst case is O of n squared, and
Okay.
its best case is omega n.
Right. That's the best you can do describing insertion sort. You can say it's O of n squared. That's the upper bound on the worst case. And it's omega of n. That's a lower bound on the best case. And also you can mention, and by the way, those are tight. You can't shrink the bounds anymore. So you can't say that insertion sort is theta of anything. You can say that the worst case is theta of n squared and the best case is theta of n, but you can't say the algorithm itself is that. And with quick sort, what would the bounds be? The worst case of quick sort. Same as insertion sort. So it's O of n squared, omega of n. No. Take that back. It's omega of n log n. Now, besides using complexity notation to put bounds on problems, on algorithms, rather, we also use it commonly to put bounds on problems. But the conventions here are a little bit different than you might expect. So when I say sorting is omega of n, the problem of sorting an array of n things into order is omega of n. What I'm saying is the worst case of every sorting algorithm is omega of n. I'm saying there is some input that will require at least linear time. Now, students all the time say, no, you mean best case there, but no, I mean worst case. Okay? So, as we study problems, we will put bounds like this on the problem. Now, you're just used to comparison-based sorting. Comparison-based sorting is sorting when all you can do is compare the elements and swap them. You can't look at the bits inside the number, do arithmetic on the keys or anything like that. So comparison-based sorting, we will prove, you probably saw the proof in 2420, is omega of n log n, which means that the worst case of every comparison-based sorting algorithm, the worst case of every comparison-based sorting algorithm is omega of n log n. So think about insertion sort. What's the worst case of insertion sort? N squared. Is that omega of n log n? Okay. What about insertion sort? What's the worst case of insertion sort? N squared. What about merge sort? What's the worst case of merge sort? N log n. You cannot make a comparison-based sorting algorithm that will do better than n log n for running time for the worst case. Now, can you make a comparison-based sorting algorithm that does better than n log n for the best case?
Yes.
Sure. For example, yeah?
BOGO sort?
Remind me what BOGO sort is?
It randomly puts things in order and then selects the
Okay.
case where it is.
Right. So if it got lucky and the first time it randomly put them in order and found out it would be done, or insertion sort. So yes, you can go faster than that bound for some of the cases. This is saying that the worst case can't be better than that. Yeah.
Perhaps I lost you with understanding why you're labeling everything as the worst case instead of best case.
Well, that's just what it means. I'm putting a... Okay, so when you invent a new algorithm, what people are going to be interested in is, how good is it in the worst case? Okay, so if...
Okay, I think I'm understanding.
And this is just a way. When I say that the sorting problem is omega of n, the comparison-based sorting problem is omega of n log n, I'm saying that no algorithm that exists now or will be discovered in the future, or I should say any algorithm that has been discovered or is yet to be discovered, can't beat that bound. That's like a universal limit. In this universe, you can't sort better than n log n, comparison-based sorting. You know, on a sequential, on a one processor machine. You know, parallel programming is a whole different issue. Now, why is it useful to prove something like that? Why is it useful to prove that comparison-based sorting is omega of n log n? Yeah.
Because once you know that that's the limit of that particular algorithm, you can utilize it effectively without spending too much time trying to improve it in ways that
Right.
you wouldn't be able to anyway.
So once you realize that you're not going to improve, you're not going to find an algorithm with a worst case better than n log n, and you have an algorithm with a worst case of n log n, like merge sort, then you stop looking for an asymptotically faster sorting algorithm and worry about other issues, you know, just trying to make it faster. You know, if you can make merge sort twice as fast, that's fine. It's still n log n, but twice as fast is twice as fast. Now, when I say comparison-based sorting is O of n log n, I'm saying something different. I'm just saying there is an O of n log n algorithm for comparison-based sorting. There exists some algorithm. I'm not saying every algorithm is O of n log n. I'm saying there's at least one. So how do you prove this? This is easier to prove than that. What's the proof of this?
Find an example of it.
Yeah, one example.
Merge sort is the example. Merge sort's O of n log n. Its worst case is n log n.
Would the best case also count as the proof?
No, for this, best case doesn't matter for either of these. I'm not saying it's unimportant. I'm saying the way these two notations are used in practice. This says the comparison-based sorting problem is O of n log n. That means that there exists an algorithm this fast. This says no algorithm will be faster than this in the worst case. So when these two bounds meet in the middle, you've sort of done the best you can, asymptotically speaking. Then you start worrying about the constants in the lower term. All right, let's prove this. How could you prove? Now remember, when you prove this, you're proving something about every sorting algorithm that has been discovered to this date or has yet to be discovered. Or, depending how you view the world, every sorting algorithm that has been invented and is yet to be invented. Yeah, how do you prove it?
Couldn't we just reason that you have to look at every element of an array?
That's exactly it. Any sorting algorithm is going to have to at least look at every element in the array. And that's going to take linear time. So you can't beat that down for that reason. This one's a little trickier, but yeah.
Yeah, I was going to say, what about for reasons like insertion sort where it doesn't look at the first element of the array and it's already moves this sort?
Well, we say it doesn't look at it, but is that true? Does insertion sort not look at the first element of its array? It definitely looks at it. When does it look at it? when it compares a second element to it.
Even if it's n minus 1, it's still order n.
True. Even if it only had to look at n minus 1 elements, it would still be omega of n, but it really has to look at all of them. The outer loop doesn't start with the first element, but it's looked at indirectly. Okay? So that's a proof of fundamental fact. Okay, so just to sum up, we use asymptotic function notation, which is, a lot of times you'll see people say big O notation, but asymptotic notation refers to all 5 of those things. We use it to put upper and lower bounds on things. And the things we put upper and lower bounds on are specific cases of an algorithm, or an algorithm as a whole, or all problems, a set of problems, a set of all algorithms that solve some problem. And what the notation means can be a little bit different depending on what you're talking about, especially in this case. This is just terminology that's been built up over the years. Okay? Yeah?
Are there problems where they found the worst case omega but still haven't matched it? Found a solution that actually gets to that?
I can't think of any off the top of my head, but I imagine there are. Maybe I can find out. Yeah.
Is there a reason that for the omega one, when it says comparison-based sorting is omega n log n, that means the worst case of every comparison-based sorting algorithm is that way? Is there a reason that that's different from the O n log n? Because I would have just assumed off the bat that that would mean the worst case of every comparison-based sorting algorithm is O n log n.
Okay, let's think about that. Why would it be futile to try to put a big O bound on every sorting algorithm? Like, what if we said every sorting algorithm is O of n cubed? Yeah?
Isn't O of any value the upper bound of the worst case, so the worst case would be?
Yeah, we're putting an upper bound, but do you know a sorting algorithm that's worse than n cubed? Yeah?
I can make one.
You can make one. Right. You give me merge sort, and how would you make one out of merge sort?
Add random lookups.
Okay.
Have a double check.
Even simpler. You just, as soon as you take merge sort and you add a loop at the beginning that loops, 2 to the n times, generates all permutations of the array, throws them away, and then merge sorts. You can always handicap a sorting algorithm, make it as bad as you want in the worst case. So when we say that comparison-based sorting is O of n log n, we mean that there is an O of n log n algorithm. A way has been found to do it. You can always find bad algorithms. Arbitrarily bad algorithms. So in a sense, this is as good as you can expect to do. When you say this, you're saying this is as good as you can expect to do. And when you say this, you're saying we have done that well. We can reach that limit. All right, let's take a break. O of G of n. We say that G of n dominates F of n. So what does that suggest? Yeah.
But it's so big that the smaller term just doesn't even matter.
Right, the smaller term doesn't matter in the long run. Asymptotically, it will become just noise. Or another way to think of it is G of n grows faster than F of n. Remember, little o is, by definition, loose upper bound on something. And so here's a table that shows you a factorial always goes faster than any exponential. Now when I say exponential, a is a constant, n is the variable. A has to be greater than 1. Okay? So any factorial will grow faster than any exponential, no matter how big that constant is. Why is that? What's the intuition behind that? What you think about it a second? Yeah?
Essentially, once n is larger than a, you're going to be multiplying larger and larger values.
Right. Yeah. With a, it's a times a times a times a times a. With factorial, it's 1 times 2 times 3 times 4. Eventually, you'll be multiplying by things in the factorial bigger than a. And it'll catch up and go ahead. Any exponential, no matter how small a is, as long as it's greater than 1, is going to grow faster than n to the a. Okay? And these don't have to be that. Okay, so a's don't have to be the same to compare them, obviously. So what that's saying is that 1.00001 to the nth power grows faster than n to the big nth power. Now, if you graphed them, what would you find? What would you find if you graphed some tiny, 1 point something tiny to the nth power? Yeah.
Polynomial would probably start out at a.
Yeah, the polynomial will start out way bigger, but eventually the exponential would catch up and just blow by it. Okay? Now, these extreme situations just don't occur in practice, by the way. You do a complexity analysis and come up with, n to the big nth power. But formally speaking, any polynomial is going to grow slower than any exponential, subject to these conditions. Any polynomial, no matter how small, will grow faster than any log, no matter what power you raise it to. So log n to the big nth will grow slower than n to any power, any positive power. And constants grow more slowly than any logarithm. So to simplify a big expression, you ignore leading constants. You get rid of leading constants. Throw away dominated terms. So you got a sum, you throw away the low order terms. And this is a rule that you have to use in situations where they otherwise don't work. So I'll come back, there's too many parentheses in that rule to describe right now. I'm going to use it in practice and then come back to you and show you what it says. So the simplification, to simplify a complex expression, you express it as a sum of terms, you remove the low order terms, you remove the leading constants, and what's left has the same rate of growth as the original. So here's an example. How would you argue that 3n squared plus 5n minus 3 grows at the same rate of n squared, using those simplification rules I gave you? Yeah? Okay, you throw away the low order terms, they're dominated by a high order term. Throw away the 3, you're left with an n squared. These are just, okay? How would you argue that n log n is little o of n squared? In other words, how do you argue that n squared dominates n log n? Yeah?
You could make the comparison that n squared is equivalent to n times n, where log of n is less than n.
Okay? That's essentially it. Let me, this is where that rule that I skipped over comes in. Let me try this. Okay, so the idea is, if you want to do this, you say that, you write the one as n times log n, and you write the other as n times n. And we want to show that this dominates that. So to do that, we have to split both sides into two pieces. And we have to show that one pair of pieces has a big O relationship. So n is O of n, right? I'm comparing this guy to that guy, and they grow up the same, or n is O of n, right? And then we take the remaining two pieces, that one, and we have to argue that log of n is little o of n. Okay? So again, what we took, we had to split both sides of this into a pair of terms such that one thing and the corresponding thing had a big O relationship, and the remaining thing and the other remaining thing had a little o relationship. So if you can do that, then you can conclude this. When it's a product. So another way to think about it is you can cancel out the things that grow at the same rate and just compare what's left. That's essentially what it's saying. Except it's saying more than that. You can cancel out things that grow even faster. So let's, what if we were trying to show that n log n is little o of n cubed? How would you do that? Using the technique I showed you. How would you rewrite both sides? Yeah.
Split it into the right side into n squared and then n, and then the big O relationship between the n and n squared.
Right. So we write this as n times log n. We write this as n squared times n. And we know that n is O of n squared. And we know that log n is little o of n. So that finishes it up. So that's what it was saying in symbols on that previous slide. Yeah?
Is there a reason to do it that way instead of saying it's little o of n squared and it's
Okay, we could have said that n is big O of n and log n is little o of n squared. That'd be okay as well. Yeah, just any way you can set that relationship. Any other questions before I go back to the slide? Yeah?
So just to be clear, little o just means that it dominates the other?
It means it grows faster than the other, strictly faster.
Is there a reason why you use big O for n is big O of n squared instead of n is little o of n squared?
Well, you got to show a big O relationship and a little o relationship. You got to split it up. So this is the, let me go back to the, so if you want to show that, if you can show that F1 is little o of G1, and that F2 is big O of G2, then you have shown that the product of the F's is little o of the product of the G's. That's what we're doing. We're sort of going the other direction. We were taking a product and splitting it up into parts so we could show that. So you got to show that one piece, two of the pieces have a big O relationship, the other remaining pieces have a little o relationship. And then you compare things. See, we're doing that because here's our table. Could we have answered the question we just did about n log n using this table?
Yeah.
Okay, how would I have done that?
You can show the same thing with a factorial and a...
But where is n log n on this table? Is it a constant? Is it this form?
Yes.
No. It's n log n. This is log n to some power. There's not an n term in this. This is a pure logarithmic. This is a logarithm raised to some power. That's n raised to some power. N log n is sort of a mixture of these two things. So when you got a product of things that are in different rows in this table, that's when you need to use this idea to simplify. So we did that. Okay, how can you show that n is little o of n log n? How do I split it up? Yeah.
Represent n as n times 1, and then we make comparisons between factors.
Okay, so we could do n times 1, and we could do n times log n. And then we know that n is O of n. That's comparing these guys. And we know that 1 is little o of log n, because our table tells us that. And that's when we're comparing these guys. That finishes it. Now, could we have split it a different way? Is there a different way to do the proof? What if we did 1 times n? Would that work?
Yeah.
1 is O of n, but then we would have to show that n is little o of log n, which is not. So in this case, we need to split it that way. Okay? Okay, this is again a mixture. We got 100 2 to the n and n times 2 to the n. We want to show that this thing grows faster than that thing, asymptotic. How do we do that? Yeah?
Split with 100 times 2n, or n times 2n.
Okay, let me get this up and you tell me again. Okay, so what's my split?
100 times 2n and n times 2n.
100 times 2n and
n times
n times
2 to the n.
2 to the n. And then what is the big O and what is the little o?
The little o is 100 to n, and the big O is 2n.
All right, so 100 is little o of n and
2 to the n
2 to the n
is big O.
is big O of 2 to the n. Yep. That's what that says.
So
Yeah.
just to clarify, you have, there has to be at least one little o
Yeah.
for the proof.
Mhm. And all these, you've got a little o and a big O.
I think it's useful to think of it like when you have your greater than or less than signs, that you always need to have the equal to in there as well, which the big O has the equal to, the little o doesn't, if that makes sense.
Yeah. Or okay. Okay, so that, sometimes you need to simplify things and it's not clear what the high order term is. This just helps you do this. Okay, so now what I've tried to give you is an intuition about how this complexity notation works before we get too tied up in the actual formal definition. So we've talked about doubling behavior and asymptotic rates of growth and rules of thumb for simplifying these things. And that's the way the people that work in the field think. They think, okay, what's the running time of this thing? Well, let's figure out the high order term. But all of those rules of thumbs that we developed can be derived from the formal definition of big O. So that's what we'll look at here. And we'll continue the next time. So this is the definition from the book. It says, let f of n and g of n be functions from positive integers to positive reals. And we can say that f of n is big O of g of n if there's a constant c greater than 0 such that f of n is less than or equal to that constant times g of n. So in other words, if you've got these two functions, we can say f of n is O of g of n if we got some way to multiply g of n by a constant that brings that graph of c of g of the n above the f graph everywhere on the positive side of the x-axis. Because we're only interested in positive integers to positive reals. Okay? Yeah?
Is this an if and only if there is a constant c greater than 0, or just c greater than 0 is sufficient to say? Or sorry, the constant...
No, it's an if and only.
Necessary, both ways?
Yeah. Okay, so let's just, I said I encourage you to think about that graphically. So let's do that. Let's draw a graph here. And let's suppose we have a function like n squared. Looks like that. Well, maybe too steep. And suppose you have another function that's like a constant. Okay? Sort of a constant. We want to show that this guy is O of this guy. How do we do that? I mean, what does the definition say? If you use that definition to prove it, how do you do it? Let's suppose let's suppose this is 1, and up here is 100. What's that definition say? Yeah?
You can multiply the n squared graph by like a constant like 100 or greater, and that'll bring up above the constant.
Yeah. If we can multiply this graph by a constant and get what's the resulting graph above here for all positive integers in, then we've shown that this is big O of this. Now notice that we only care about what happens at the positive integers. It says the function we're talking about code for positive integers and positive reals. So what would happen if we multiplied that n squared graph by 100? What would it look like?
It would just lift.
I mean, it would still start at 0, because 0 times 100 is 0. It would cross right here, so it would, I don't know, it would be a lot steeper. It'd be something like that. But the book definition doesn't care about this part of the graph. It just cares about what happens at the integers. Yeah.
So the first curve you drew is f of n?
Yeah.
And then the second one would be g of n?
This is f of n. I'm sorry. This is f of n. That is f of n. And this is g of n. And we're trying to show that f of n is big O of g of n. And to be concrete, let's say we're trying to show that n squared is O of 100. No. Scratch that.
Wouldn't it be the other way around?
Yeah. We're trying to show that 100 is O of n squared. So it doesn't require n squared to always be above 100. It requires that c times n squared always be above 100 at the positive integers. So we just multiply it by 100 to get this thing up here at the integer 1. So that's the book definition. This is the more traditional definition. Let f of n and g of n be functions from reals to reals. So not, before it was from positive integers to positive reals. This is from reals to reals. We say f of n is O of g n if there are positive constants c and n naught, such that 0 is less than or equal to f of n is less than or equal to c of n for all sufficiently large n, all n greater than or equal to n naught. That's a more complicated definition, but it's the one we're going to use because it's a lot easier to work with. Okay? So let's focus on the differences. The functions are from reals to reals. We don't just care about what happens at the integers. And we have to find two constants, c and n naught. Or another way to think about it is we get to pick two constants because this n naught makes our life easier. What does n naught do for us? We have to show this inequality. We have to show that g of n is not negative, and we have to show that c of g of n is bigger than f of n. How does n naught pay off for us? Yeah.
We get to choose our starting point.
We get to choose a starting point. We can say, I don't care what happens, until we get to 75 or something. Let's just that's the big payoff. That makes things a lot simpler for us. So we will. We already saw that. The definitions are equivalent, but the traditional it's just easier to work with. So here's an example. There's f of n up there. And here's g of n right here. So the question is f of n O of g of n? Is g of n O of f of n? Which, if either, is true? Something just went haywire. Sorry. Okay, so right there. So tell me, is the blue curve O of the red curve?
No.
Is the red curve O of the blue curve?
Yes. Yes.
Well, let's start with that. Suppose we wanted to prove that the red curve was O of the blue curve. So we have to come up with a constant we need to say something like this. We need to prove that 0 is less than or equal to, what is the red curve? The red curve is G. Sorry. I want to actually, so it's, G of n is just 1. So we want constant times 1 to be less than or equal to, I'm having a good day here. And that's what we have to show. We have to show that the red number, 0 is less than or equal to the red line, which is less than or equal to some constant times the blue line, for all n bigger than some n naught that we're going to pick. So we just have to convince ourselves that that's true for a given c and a given n naught. So it's not the case that n and n naught will be unique, necessarily. So what's a c and an n naught that works?
1 and 1.
1 and 1. Okay, so let's let C be 1. So just get rid of that. And we'll let n naught be 1. Okay, so do you agree that's true? I mean, you can just see it from the... Does this thing ever get less than 2? Does this thing ever get bigger than or less than 1?
No.
No. So the red thing is always bigger than 0. It's always less than that thing, because that thing is never less than 2. And that's true starting at 1 all the way to the end. It's true starting from 0 all the way to the end. It's true starting from 1,000,000 all the way to the end. Any of those is sufficient to prove that the red line is O of the blue line. Okay? Any questions about that one? Yeah?
Could it work the other way around if we scale the 1 over n plus 2 by one's worth or something like that?
It does work the other way around. But let me see if there are any questions about this, and we'll do that one. Okay, let's try the other way. So what is it we have to show if we want to show that the blue line is O of the red line? First of all, why does it make sense that the blue line is the same as the is O of the red line?
Because 1 over n goes to 0.
Okay? So ignore what's going on over here and just look from this point on. Would you say those are growing at the same rate? Yeah, as you go to infinity, basically this thing flattens out too. They're growing at the same rate. I.e. not at all. So in fact, they're theta of each other. So, but what is it you formally have to prove for that? First of all, how's our rule of thumb help us here? Our table didn't have an entry for 1 over n. But any constant dominates 1 over n, because that goes to 0. So basically, we can throw out this thing, because it's a low-order term, and we're left with 2 constant functions that have the same doubling behavior. Okay? What's the thing that we have to prove, though? We're working from the first definition. So we want to prove that blue is O of red. Yeah? Well, let's write it in symbols first, and we'll plug in the constants. So 0 less than or equal to 1 over n plus 2 less than or equal to some constant times 1 for all n greater than or equal to n naught. Okay, let's let n naught be 0. Is there any constant we could multiply this by that would make this line be above the blue line for everything greater than or equal to n, everything greater than or equal to 0?
Multiplied by 3.
Well, but 3, okay, multiply by 3 we get up to here.
Yes, and then,
But it's not bigger than this yet.
then you make n naught equal to 2.
Well, I said if n naught is 0. What's the problem making n naught 0?
It's infinity.
Asymptotically approaching this.
Right, it's approaching infinity at 0. We multiply this by a constant, we're never going to make this thing be above something that's approaching infinity. But the beauty of the n naught is we can ignore this part of the graph. Let's just chop it off here. Let's chop it off at 2. Let's let n naught be 2. Now, we got to pick a constant so that this line gets above the blue line from 2 all the way to the right. That's the beauty of the n naught. It simplifies our life. So what can we multiply? What is the value of this thing at 2? It's 1 over is 2.5. So that's our c, right? We could let c be 2.5. 5 halves. Or anything bigger. And that's a true inequality. You can just see it off the graph. So if we multiply that by 5 halves, we get this curve. We get the red one looking like this. And they cross at 2. And from 2 on to infinity, the red line's above the blue line. So we're good. That's the formal proof of big O-ness. And you can use it to prove all the other things we talked about today. We'll look at a few more of these examples next time, and then move on to something new.